4A Introduction to Mechanics. 4.1 Historical Development of Mechanics. Several centuries before the birth of Christ, Greek philosophers believed that matter was motivated to behave in certain ways. Solid matter desired to move toward the center of the world, so solid objects fell toward the ground. Light matter desired to ascend to the heavens, so smoke and vapor tended to rise. According to Greek philosophers, all natural phenomena and matter acted according to mysterious internal tendencies. Because of the presuppositions inherent in their model of the natural world, most Greeks, including Aristotle, could not conceive that inanimate physical principles cause natural phenomena. As Chapter 2 discusses, Aristotle's teachings became the basis of European science for more than 2,000 years. One of the first to successfully challenge the Aristotelian worldview was the Italian scientist Galileo Galilei. In the 17th century, Galileo argued that rather than assume that mystical motivations animate matter, scientists should examine how things move and then describe their motions in mathematical ways. This method was a radical departure from how nature had been studied in the past. Many natural philosophers gladly accepted his ideas and began to make real scientific progress. Others were less enthusiastic because many of Galileo's ideas seemed to contradict the doctrine of the Catholic Church. Some Catholic leaders accused Galileo of heresy. The scientific revolution begun by Copernicus a century earlier rapidly moved forward as Galileo described motion and provided observational evidence for a mechanical, sun-centered model of the universe. Sir Isaac Newton continued this revolution in the 18th century. However, a more complete model of the causes and effects of motion and other processes wasn't introduced until the early 20th century by Albert Einstein. The modern study of motion, called mechanics, is based largely on Newton's three laws of motion and his law of universal gravitation. Today, physicists split mechanics into three parts: kinematics, the description of how things move; dynamics, the description of what causes things to move; and statics, the description of how stationary things react to pushes and pulls. As you study mechanics, you will encounter many terms and concepts that are familiar to you. However, you may not have a sound understanding of what they mean. Before exploring the fascinating world of kinematics, you need to understand the key terms of mechanics. You will also learn how engineers use the laws of motion to improve vehicle safety, especially for children. 4.2 Physical Systems. In mechanics, as in nearly all of science, scientists must first clearly define what they are going to study. This helps them decide what factors they must take into account, both in their experiments and in any scientific models they develop. They mentally construct a boundary that clearly defines the limits of the objects or processes they are studying. The boundary may be an actual surface, such as the walls of a container, or it may be an imaginary box. Everything inside this boundary is called the system. All processes, forces, and immeasurable properties originating within the boundary belong to the system. Everything outside the boundary is the system's surroundings. In most cases, scientists are interested in how the surroundings affect the system. A system can be anything you are studying. Some examples include a baseball, a pot of water, a volume of air, an elevator cab, an airplane, a light bulb, or even your body. For our Dominion science problem, the system under study is a child traveling in a car. In mechanics, we can identify the pushes and pulls on a system and then observe how the system responds to these influences. In the discussion of kinematics later in this chapter, the system and its boundaries are clearly identified so that you can learn how to identify them for yourself. After studying dynamics in Chapter 5, you will be able to recognize the system of interest within its boundaries and the causes of motion imposed on it. 4.3 Frames of Reference. American pioneers often crossed stretches of deserts on their westward journey. Sometimes a group of travelers lost the trail and wandered until they ran out of water and died in the arid wasteland. A water hole might have been just a few miles away, but without landmarks to guide them, people were often misled by the vast, trackless desert. In kinematics, we need landmarks to anchor our observations. Without them, our studies are as futile as the lost pioneer's wanderings. Physicists call such landmarks points of reference. A point of reference is nothing more than the stationary location from which we choose to make our observations. The geometric space containing the point of reference is the frame of reference, or reference frame. In the study of motion, the frame of reference determines how motion will be described. For example, how fast are you moving right now? Suppose that you are sitting at a desk in a classroom in Baltimore, Maryland. A person in the same room would say that you're stationary because his reference frame is the classroom. However, if he were somehow suspended high above the earth and could observe your school from that location as the earth rotates in space, he would say that you were moving at 360 meters. In that reference frame, the positions of the earth and sun are fixed, but the earth is free to rotate about its axis. If our observer were moved to a point in space far above the sun's position relative to the plane of the earth's orbit, he would observe the earth whirling around the sun at almost 30,000 nanometers. Your motion would be a complicated snaking motion superimposed on the earth's orbit. That point of view places the sun in a frame of reference at a location that is stationary in relation to the background stars. When describing motion in mechanics, no single reference frame is more correct than another. The way motion is observed depends on what you choose as the frame of reference. The choice is determined somewhat by the kind of motion you are studying. You pick a reference frame that makes the study of motion easiest. Kinds of reference frames. Scientists generally choose a reference frame where they know the causes of motion and where moving systems follow the laws of motion, which you will study in Chapter 5. Systems move in straight lines or in simple curved paths caused by forces acting on the systems from within the frame of reference. We call such a reference frame a fixed or inertial reference frame. We assume such a point of view is stationary, even though it may actually be moving at a constant speed in one direction. For instance, as a car passenger, you watch cars passing your car on a highway from an inertial reference frame, as long as your car's driver maintains a constant speed. The motions of systems that you will study in this course will use an inertial reference frame. When the observational point of view is not moving at a constant speed or direction, it is accelerating. We are then observing systems within an accelerated reference frame. Continuing the above example, when your car's driver slams on his brakes, everyone in the car jerks forward. The passenger's motion seems to be the result of a force suddenly acting on them. But the force isn't real. It results from the deceleration of the car, which is the reference frame in which you are viewing their motion. Scientists often observe systems from a reference frame that is not stationary and in which the speed or direction is changing. This is the case when meteorologists observe the motion of weather systems from a point on the rotating Earth's surface. Air masses should flow directly from regions of high pressure to lower pressure, but an apparent influence seems to turn them from a straight path. In the northern hemisphere, they twist to the right. In the southern hemisphere, they deflect to the left. This is called the Coriolis effect, and it affects everything moving on the Earth. Every point on the Earth's surface lies within a rotational reference frame, which is a special case of an accelerated reference frame. The apparent forces you feel while riding a spinning merry-go-round aren't real, but you sense the effect within the rotating reference frame of the playground ride. The coordinate axis. We measure straight-line motion of a system in relation to a coordinate axis. A coordinate axis is an imaginary line marked off in distance units. We often choose its direction to point in the direction of motion of the system to simplify our study. A coordinate is a value of the system's position along the axis. The origin of the axis is at the 0 position on the axis and is the point of reference for determining position. We usually choose to have coordinates increase to the right for horizontal axes or in the upward direction for vertical axes. Coordinate values increase in the positive and negative directions from the axis origin. This introductory course covers only straight line, one-dimensional motion. Studies of the other kinds of motion and their specialized reference frames require more advanced mathematics than you are likely to know at this point in your education. As you learn each new concept, relate it to one-dimensional motion. 4.4 time intervals. We can define time as a non-physical continuum that orders the sequence of events and phenomena. Let's examine this technical description of time. Non-physical simply means that time can't be touched. It's not matter. A continuum is a scientific word for an unbroken expanse or series. Time is continuous. Without the existence of time, we couldn't experience the world as a series of events. Every instant would be now. We would have to be like God, who is outside of time, to experience the world. We can infer from the Bible that time began the instant God began to create the heavens and the earth. The Bible even starts with a time-related phrase, in the beginning. Time will likely continue into future eternity, since as created material beings, we will exist, think, and move forever. Therefore, time is a continuum that began at creation and will continue into the future without end. Any natural phenomenon must occur within a span of time. A time span has an initial time, t.i.e., and a final time, tf. The length of a time span is an interval. A time interval is represented by the symbol triangle t, spoken delta t, and is calculated by subtracting the initial time from the final time. A time interval is always a positive number because a later time always has a larger positive value than an earlier time. Correctly identifying time intervals is an important part of understanding how things move. For example, time intervals in car accidents can make the difference between a minor injury and death. An adult human skull can bear a load close to 1.5 tons for a fraction of a second. But if the time interval is longer, the skull can be crushed. 4.5 Scalars and Vectors. In physics, certain dimensions require just a single piece of information to be complete. These are scalar quantities. You are already familiar with many examples of scalars, such as the volume of a soft drink can, 355 nm, the temperature outside, 12 degrees C, the time of day, 10:55 a.m., and the mass of a brick, 1.5 kilo. A scalar dimension can be positive, negative, or zero. Other dimensions that physicists use require two pieces of information to describe them completely. These quantities are vectors. A vector is something measurable that includes both a scalar value and a direction. For example, the weight of a 20N box is a force vector of 20N directed straight down. A car moves down Main Street with a velocity vector of 15 ms east. The scalar value of the weight or velocity alone cannot completely describe these quantities. The direction of each is also necessary. A vector has a direction measured relative to each coordinate axis in the observer's frame of reference. In straight line, one-dimensional motion, a vector may point only in the positive or negative directions. So we will indicate vector quantities by their positive or negative scalar values to simplify concepts in this textbook. When we show a vector quantity in a diagram, such as figure 411, we use an arrow pointing in the direction the vector affects the system.